These notes are to help out with things that are moving at a constant speed or a constant velocity. So as we discussed in class, there's a difference between velocity and speed. Although they're closely related, there is a difference. So we know that speed is a measure of how fast something moves, right? And we said that it is a rate, and all that means is basically it's something measured over time, right? It's meters per second, so it's a rate. Rates are quantities divided by time. In addition, speed is a scalar quantity, and we discussed what scalar means, and we'll get into what a vector quantity means also. But basically what scalar quantity means is it has no direction, meaning if I say go 50 miles per hour, you can get in your car and you can drive north, west, south, east, northwest, southwest, etc. at 50 miles per hour, and you would have a speed of 50 miles per hour. Now, that isn't true for velocity. So velocity is also a rate, right? So it's measured with respect to time, but it says the rate that displacement changes with time. And that displacement is different than distance. So it says here, right, the key thing here is that velocity is a vector, not a scalar quantity. And what that means by a vector quantity is it has magnitude, and that word kind of confuses people, magnitude. Basically, that's just the number 50 for 50 miles per hour, 15 for 15 meters per second. But what it also has is it also has direction, which means if I said drive 50 miles per hour, that's a speed. But if I said drive 50 miles per hour straight north, now it's a velocity, but because it includes direction. So when we talk about speed, we don't care about the direction of motion. The car went 50 miles per hour. We don't care if it went north, south, east, or west, or whatever. With velocity, we do care about the direction. Velocity would be the motion of the car that it is going. Let's see here. And for the notes, I picked south at 35. So right, you can, if I tell you to go south at 35 miles per hour, then you have that direction. You can't just go wherever you want to. You have to specifically go south. And our standard units are going to be in meters per second. So it says, right, vector is magnitude and direction. So the number of 35 is the magnitude, and the south gives you the direction. So in our example here to the right, we have a train that's going around a track. It says the toy train is traveling around a circular track. It is moving at a constant speed. It does not have a constant velocity, right? Because the direction is changing. It's not, that train is not always going south or always north or east or west, etc. Because it's moving in a circle, it's changing direction. Therefore, it's not moving at a constant velocity, even though it's moving at a constant speed. So you really have to be careful with direction. Okay, distance is a scalar, meaning it has no direction. We earlier, and I said that in the notes, we are using displacement. So displacement, of course, is a vector, which means, right, what is a vector? It's magnitude and direction. So its magnitude is going to be the distance, but you have to add in that direction piece. So you traveled 30 meters north, or you traveled 45 meters down, or 13 meters to the right. There has to be some form of direction in there. And for us, we are going to use meters as the standard measurement. Be careful with displacement. It's always a change. It'll also be called the change in position. Essentially, this is two ways of saying the exact same thing. Whenever you want to find the change, it always has to be the final position minus the initial position. It cannot just be the difference. It has to be final minus initial. Okay, when we start putting them in equations, we have to show direction. So what we're going to do is we're going to use positive and negative values to show this direction. So as an example, let's say you have this car in this picture and it's going from A to B, right? We can say it's moving in a positive direction, so it would have a positive velocity, and its change in position, change in position, right? It's always final minus initial, so we would say it ended at 50 and it started at 30, so its change in position would be positive 20. And what that's telling us with the positive 20 and the positive velocity is it was moving this way according to the scale that's set up, or to the right. If you look at the other example here, let's just look at when it was moving from, let's say, point E to point F. It went from negative 40 to negative 50. It's moving in a negative direction, or it's moving in the opposite direction of our other car. So we designate this direction as positive and this direction as negative. And you can set whatever way you want for negative and positive, but usually you make to the right positive, to the left negative, kind of like a graph, right? If you had a graph, this would be the positive x-axis, this would be the negative, so we kind of keep along with that. So for the change in position for that car, right, it ends at negative 50, it started at negative 40, so final minus initial, right, that gives us a change of negative 10 meters, meaning because it's negative, we know it moved further to the left when compared to the origin instead of to the right. So that's where those negatives and positives come into play. Okay. Let's see if I can spell this right. Okay, instantaneous velocity is the velocity of an object at any given instant in time. Well, for us, they're always moving at a constant velocity, so the instantaneous velocity matches up with other instants in time, right? Because it's always going the same. But if it does change, we could find an average velocity also. So you've just got to be careful whether you're looking for instantaneous or average. Just realize that whenever we use that equation that we came up with, and just ignore this t here, I'm not sure what that was, we have the average velocity is change in position over time. Now this has to be the change in position in this time interval. You know, if something travels, let's say it travels 100 meters, and they ask something about what was the average velocity from 2 to 4 seconds, right? Well, you didn't travel 100 meters in 2 to 4 seconds, you traveled 100 meters total. So be careful there that the change in position has to match up with the specific time interval that you're talking about. So in the equations, right, a lowercase v is for velocity. Make sure it's lowercase, not a capital. A capital V is for volume. Notice that sometimes for average they might put a little line over it. You're not going to see that much, but if you see it in a textbook, it's saying average. So what we end up with, if you're just using symbols, right, is that the average velocity is the change in position or the displacement over the change in time, but usually people just put time instead of change in time. So that equation, again, it's good for something if it's moving at a constant velocity, or if you want to find the average velocity of something, it's also good. Just make sure you do the total change in position over the total time if you wanted to find the average. Okay, looking at page 2. Right, if the initial conditions are 0, in other words, the motion started at time 0 and a position of 0, then the equation for average velocity can be shortened to v equals x over t. This is also used when an object has a constant velocity. So there's different variations. You're going to see the same thing written different ways. Some people write it this way. That's not very common. More people will tend to write it this way, and occasionally you will see it written like this, right? Because remember that this change in position, right, is the final position minus the initial position. But on the AP exam, whenever they're talking about a final, they basically leave off the subscript as in this portion of the equation. They don't put xf, they just put x. If they're talking about a final velocity, they just put v. They'll put a v initial and a v instead of a vf. I tend to put a vf on there just so I can keep them straight. Okay, so some example problems, right? We have in 1988 Summer Olympics, Florence Griffith Joyner won a 100-meter race, so we know that this is the displacement, right? Or the distance traveled, 100 meters, in a time of 10.5 seconds, so we know that's the time. Assuming the distance was laid out to the nearest centimeter so that it was actually 100.00 meters, what was her average velocity in meters per second and kilometers per hour? Now just realize a lot of times velocity and speed are going to be interchangeable. If they say what's the speed, just use this equation. But basically you could think of, instead of change in position, you could think of distance equals speed times time. Okay, so looking at the equation, whenever you are going to do anything in the class, you always need to write out the equation first without any numbers. They give you points for that on the AP test. So we have v equals delta x over t. Then we can just plug in our numbers. That's considered showing our work, as just plugging in the numbers. Remember, it's a 100-meter race, and you don't have to write in the units, but it was in 10.54 seconds. So 100 divided by 10.54 is 9.49 meters per second. And that's your answer. I usually round all my answers to 2 decimal places. They really don't care on the test. You don't have to use significant figures or anything like that. If they did want you to convert it to kilometers per hour, right, this is just a little example of your kind of what you did in chemistry when you're doing stoichiometry, when you're doing conversions, right? You go 9.49 meters in 1 second. So if we were going to convert that, right, we know that there is 3,600 seconds in 1 hour. That gets rid of our units of seconds. So now we would be in meters per hour, and we want kilometers. So we also know that there is 1,000 meters in 1 kilometer. So now the units of meters cancel out, and you get your answer in kilometers per hour. So number 2. You begin a trip and recorded the odometer reading. It says 45,545.8 miles. You drive 35 minutes. At the end of that time, the odometer reads 45,569.8 miles. What was your average speed in miles per hour? Well, our units normally are meters per second, but here they give us miles and minutes. So if we use that, we will end up in the units of miles per minute. We want miles per hour. So what I would do is I would quickly convert your your minutes into hours, but you could also solve it and then convert at the end. Just depends on how you want to do it. So using that same equation, remember that V is delta x over t. Well, delta x is the final minus the initial position over the time. Right? Remember that we ended here. So 45569.8 minus the initial starting point over the time of 35 minutes, and that gives us our answer, 0.69 miles per minute. Right? And now you would, just like we did up in here, you would have to convert your miles per minute to miles per hour. So if we are 0.69 miles in every 1 minute, right, we know that there are 60 minutes in 1 hour, so the units of minutes cancel, and you are left with roughly 41 miles per hour. And again, I rounded. The test says you can use anywhere from 2 to 4 significant figures. Again, I usually go to two decimal places, and they don't care. They're not going to mark you wrong for it either way. Okay, a high-speed train travels at an average speed of 227 kilometers per hour for 2 hours. So we're in kilometers per hour. We're in a unit of time of hours, so that's good. Those match up. It takes 15 minutes. We're in a different unit of time for passengers to exit and enter the train. It then travels at 220 kilometers per hour for 1 hour. What is the train's average speed? Okay, well, the common mistake that people make here is that they will go ahead and take the 227 and the 220, and they will average numbers together. 227 plus 220, and they divide by 2. That doesn't work because you traveled at different speeds for different amounts of time. So to find the average velocity, it has to be the total change in position over the total time that the object moved. Well, if it moved at 227 kilometers per hour for 2 hours, hopefully you can kind of see, again, you could really use that equation. It traveled for, what would that be, 454 meters, right, in 2 hours, and it was a time of 2 hours. It then traveled at 220 kilometers per hour for 1 hour, so it traveled another 220 kilometers in 1 hour. And then it didn't go anywhere, right, in 15 minutes, and 15 minutes, of course, is 0.25 of an hour. So when you put that in your calculator, you end up getting that the average speed was 207.38, and we were in kilometers per hour. So it's that doesn't really make sense, does it? Hold on here. Nope, I checked that in my calculator. That's right. So it's 207.38 kilometers per hour, and it must be lower than both of those because of the 15 minutes of sitting still. So that's an example where you're using that equation for the average velocity instead of just the velocity in one scenario, right? You have two different things that were going on there, traveling at two different times at two different speeds and then sitting still for 15 minutes. Number 4, the good news about number 4, if it was last year in AP Physics B, we would need to do hard problems like this, but in AP Physics 1, we do not need to do anything that challenging anymore. So that's great. Okay, all motion is relative. Looking at, we should be on page 3 now. Okay, motion velocity is said to be relative. This is an important concept. What it means is that when we say that something is a given velocity, that velocity is relative to something else. So what happens is, right now you might be sitting down. Well, you think, okay, well, you're not moving. Well, relative to your house, you're not moving. Relative to the earth, you're not moving. But relative to the moon, you are moving. Right? Because you're traveling around the sun, because you're on the earth. And the earth is traveling around the center of our galaxy, the earth is traveling around the sun, and our solar system is traveling around the center of our galaxy. So even though you're not moving because you're sitting still in your house, you actually are moving because you're actually moving really, really crazy fast because you're orbiting around the sun, and then as a solar system we're orbiting around the center of our galaxy. So we're actually moving really close, and that's kind of that relative velocity piece. It depends on your frame of reference. What are you comparing your velocity to? So just a little example, right? If you're a passenger in an aircraft and you are traveling over 500 miles per hour, right, over the earth, well, then you're moving at 500 miles per hour, right? That seems to make sense. But you're moving at 500 miles per hour relative to what? You're moving at 500 miles per hour relative to the earth. But what about that guy that's sitting in the plane next to you? What are you traveling relative to him? Relative to him, you're not moving. So you would have no motion relative to the plane. So it depends on your frame of reference. Right now you could have a velocity relative to the plane, right? It says unless you get up and go walking in the aisles. Now all of a sudden you do have a velocity relative to the plane. So let's say you're walking in the aisle at 3 miles per hour. Depending on which way you're going, relative to the plane you're just moving at 3 miles per hour. But relative to the ground, right? So your motion relative to Earth, depending on what way you're walking, it could be 503 or 497 miles per hour, right? Because you're walking up and down the aisleway. Okay, we talked about position versus time graphs, right? Hopefully you remember from the lab that we had a graph that was a linear line when we're moving at a constant velocity, and because of that we use the idea that y equals mx plus b, right? That is the equation for the graph for a linear line. So using that equation we were able to come up with our own equation. Let's see, right? We know that b is the y-intercept, and this y-intercept is actually the starting position, right? And m is the slope. So we said that since we are graphing displacement on the y-axis, right, our change in position in meters, the change in x is simply the change in displacement, or delta x, right? We have delta t on the x-axis, and so if the slope of something is the rise, right, or change in y over the change in x, we can look at it and say, well, what is the change in y over the change in t, right? It ends up being, right, it's our change in position over our change in time, which we said is velocity, right? Change in position is in meters, change in time, of course, is in seconds, so you'd get meters per second. So the slope of the line, right, is the velocity, and if your delta x is in meters and your t is in seconds, it's in meters per second. So if that is true, and we're looking at this graph here, right, we can look and say, okay, well, at a little more than 10 seconds, we're at a position of 5 meters by following that point over. And you could do that for anything. Where were you at 5 seconds? Well, at 5 seconds, you were a little bit more than 2 meters away. Right? If you find the slope of this line, you will find the velocity. And remember, it's velocity, and so the slope of this line is positive, so you know that the object has a positive velocity. And usually by a positive velocity, you can kind of say it's moving to the right or it's moving up. And sometimes it's just really generic and you'll say away from the origin, right? Because the origin is 0 meters. So our last thing here says, what is the velocity of the object whose motion is depicted in this graph? Well, if you pick a point and let's say you use the 5 meters here, we know that the slope represents the velocity and the rise would be delta x, right? So if we end at a position of 5 and we started at the origin, because that's the y-intercept, the time that went by, let's say, is 10.4 seconds, and so therefore the velocity or the slope of that line is 0.48 meters per second, right? So we should be able to look at this graph. Let's see if I can get rid of all of this stuff, and you should be able to look at the y-axis to see your position, the x-axis to see your time. The slope gives you the velocity, so at any point, again, you can pick and say, okay, well, at 7 seconds, that's the position you were at, right? The y-intercept, or where you are at 0 seconds, tells you your position when you start. And that's it.